Okay, we are right on time. So over to you guys.
Okay, so welcome everybody to the session 11 of CHESS, which is SCA of Public-Key Schemes. Elke de Mulder and myself are the session chairs here. We have 6 papers to present in this session. And the first one is by Prasanna Ravi, Sujay Sinha, Anupam Chattopadhyaya, Shivam Bashin, and it's titled Generic Side Channel Attacks on CCA, Secure Lattice-based PKE and Chems. So presenter will be Prasanna Ravi. So please go ahead, Prasanna.
Thanks for the introduction, Timo. Yeah, so I'm Prasanna Ravi. Hello, everyone. I'm from Nanyang Technological University, Singapore, and this work was jointly done with Sujay Sinha from University of Birmingham, Anupam Chattopadhyaya and Shivam Bashin from NTRU, Singapore. And in this work, we basically propose generic side channel assisted chosen ciphertext attacks against 6 lattice-based public key encryption and key encapsulation mechanisms, and all the targeted schemes were basically second-round candidates in the NIST standardization process for post-quantum cryptography. Public key encryption schemes are known to be susceptible to chosen ciphertext attacks, especially when static keys are used, which we refer to as a key reuse scenario. And the shared key, and these schemes are typically used to perform secure key exchange in several protocols such as the TLS. And the shared keys are basically obtained by performing known transformations over the decrypted message. So it's pretty simple there. And when you plug these schemes into protocols, one can easily check whether the shared key is actually matched or not. So it's possible to easily instantiate something like a key mismatch oracle to simply check for the key mismatches. And in such a setting, what an attacker can do, or how chosen ciphertext attacks typically work, is that you can craft malicious ciphertexts, and the attacker can subsequently make several guesses for the decrypted message and subsequently the shared secret key. And he can simply query the key mismatch oracle to check whether the key actually matched or mismatched and so on. By doing that over several such malicious ciphertexts, an attacker can easily obtain the secret key by simply having information about the key mismatches. Now, lattice-based schemes are also known to be susceptible to such chosen ciphertext attacks. And most public key schemes adopt concrete chosen ciphertext security mechanisms to offer protection against such attacks. And the Fujisaki-Okamoto transform is one such CCA secure technique that's been adopted widely by many lattice-based schemes for chosen ciphertext security. And the way it typically works is by simply checking for the validity of the received ciphertext. And if the received ciphertext is valid, then the FO transform generates a shared secret key, which is always correct. However, for an invalid ciphertext, the FO transform checks for the validity of the ciphertext and detects it as invalid and simply aborts the procedure or just generates a pseudo-random key. So as a result, what happens is that the attacker for an invalid ciphertext cannot gain any information about the decrypted message. And this essentially removes the presence of a key mismatch oracle, and hence it provides concrete security against such chosen ciphertext attacks. But in practice, this assumption only holds in a black box setting. However, one can ask a message or ask a question if it's possible to obtain information about the decrypted message utilizing side channel information. In this work, what we show is that it's possible to efficiently instantiate side channels as a plain text checking oracle or a key mismatch oracle to perform efficient chosen ciphertext attacks over 6 lattice-based public key encryption and key encapsulation mechanisms. And as stated earlier, we target 6 lattice-based schemes, and all the schemes are based on the well-known learning with the error and the learning with the rounding problem. And all the schemes are second-round candidates in the NIST call for post-quantum cryptography. I'd like to summarize the attack in a single slide here. So this is how a CCA secure decryption procedure looks like. So you have the decryption procedure that decrypts the ciphertext to either a code word or a message. And all the targeted schemes are associated with a certain decryption failure probability. So some schemes utilized error correcting codes to reduce the decryption failure rate. So the decryption procedure returns a code word from the ciphertext, and the ECC procedure is applied over the code word to get back the message, and the message is subsequently passed to the effort transform to generate the shared secret key. Some schemes, however, do not utilize error correcting codes. So the decryption procedure simply returns the message which is passed to the effort transform to generate the shared secret key. Now, the attack works as follows. So we show that it's possible to craft malicious ciphertexts such that they can always decrypt to only two possible values, irrespective of the value of the secret key. So the code word can only take two values, A or B, and similarly, the message also can only take two values. And we also show that the value of the decrypted messages also share a very unique relation between the different candidates for the secret coefficients. So all the schemes deal with polynomials. So we show that the value of the decrypted message basically has a unique relation with the individual secret coefficients, and the way through which the attacker gains information about the decrypted messages using side channels as stated earlier. So in schemes such as round 5 and LAC, the attacker can target certain operations within the error correcting codes. And in other schemes such as Kyber, New Hope, Frodo, the attacker can target operations within the effort transform to basically differentiate or to identify the value of the decrypted message, whether it is A or B. And the attacker can similarly make several such queries using malicious ciphertext and can subsequently recover the full secret key. And in this work, we basically propose such generalized chosen ciphertext attacks using side channels on. So I'd like to summarize our experimental results here over 3 schemes. And we can see that the number of traces required number in several thousands, and the total time required to perform the attack is also very practical, ranging from 4 minutes to 10 minutes. So yes, so this basically concludes my presentation. Thank you, and if please feel free to ask any questions. Thank you.
Are there any questions from the audience? I'm not seeing anything yet. I did have a question though. In your, I went through the presentation and I saw that, so you're mostly focused on templates in this work. Is that's correct, right?
Yes. So we build templates for the different decrypted messages, and then basically do a template matching this.
Are you going to follow up with more DPA style attacks, or what, or is this was this your main focus right now?
All our attacks were performed on unprotected implementations. So the and masking is actually a concrete countermeasure against our such attacks. So we could potentially extend our work to masked implementations. And as I had mentioned earlier, we had utilized side channels to instantiate a key mismatch oracle. So the attacker can only gain binary information about the message, whether this was this or that. So an attacker can potentially gain more information about the decrypted message through side channels and could potentially reduce the trace complexity of our attacks.
Yeah, that makes sense. Thank you.
Okay.
I also have one question. So
yes.
You provided these experimental results only for Kyber of all the NIST finalists. So what about Saber and Frodo? Are they in line with that?
Yes. So our attacks can also extend to Saber and Frodo in a very similar manner. Frodo in particular is different from all the other schemes that we have targeted. Frodo is based on the standard LWE problem. In fact, in the paper, we show that we take advantage of certain efficient properties of polynomial multiplication to reduce the trace complexity. And those techniques only don't apply to Frodo because Frodo only performs a matrix vector multiplication. So apart from the trace complexity, the attack technique remains the same.
Yeah, thanks.
Okay, thank you. Thank you very much. Yeah. So I'll stop sharing. Yeah, thank you.
Okay, and then thanks, Prasanna. The next talk will be about Blue Thunder, a two-level directional predictor-based side channel attack against SGX, and it will be it's a paper authored by Tianlin Huo, Xiaoni Meng, Wanhao Wang, Shungliang Hao, Bai Chao, Jian Chai, Mingxun Li, and the speaker will be Tianlin. So please.
对不对这个？哦 ，eyes. Sorry, can you see?
At least I don't see the screen at the moment.
Oh. 开启上。
Okay, I can see your face now, but try to share the.
Eyes.
Okay, now it says that you have started screen sharing, but I don't see the slides.
You didn't see slides, yeah?
No, at least I don't.
Oh, let me check. Oh.
You may need to share the full screen or the desktop. It's usually in the upper left-hand corner as an option rather than a single application.
Oh, you see the slide?
No.
No, sorry. Oh. Oh. So
maybe it's a bandwidth problem.
How about this time?
No.
Oh, sorry. So just let me see.
Do you have several desktops and it's maybe?
Oh, can you?
Or no, it's just a blank screen that I see now.
A blank screen?
Black screen, yeah.
Oh. This time work?
Nope.
Could we maybe
Maybe
email the
I was looking, so you don't have these slides here in the program that I could share it from my screen.
Yeah.
No.
Or we can move on to the next presentation and
yeah, let's do so and try to figure out how the problem gets solved. So we put Tianlin for hold for a while and take the next paper now. So okay, so so the next paper will be titled "Strengthening Sequential Side Channel Attacks Through Change Detection," and it's written by Luca Frittoli, Matteo Bocci, Silvia Mella, Diego Carrera, Beatrice Rossi, Pasqualina Fragetto, Ruggero Susella, and Giacomo Boracci. So please.
Hi, can you hear me?
Yes.
Can you see my screen as well?
Yes.
Okay. Hi, everyone. My name is Luca Frittoli. I am a PhD student at Politecnico di Milano, and I also work in collaboration with ST Microelectronics. The title of our paper is Strengthening Sequential Side Channel Attacks Through Change Detection. Sequential attacks are a particular kind of side channel attacks in which the attacker tries to reconstruct the secret key, one bit or a chunk of bits at a time, by taking in each step the key value maximizing a certain distinguisher function. The attacker also has to reconstruct the intermediate results computed by the target algorithm, which are necessary to compute the distinguisher function. For this reason, when an error occurs in the reconstruction of the key, also the corresponding intermediate result will be wrong. And so all the following guesses will not be reliable because they will be based on a wrong assumption over this intermediate result. So the error, we can say that the error propagates throughout the attack. A consequence of error propagation is a distribution change in the distinguisher. So if we take the maximum distinguisher value in each iteration and we plot it on like we did in this case we had correlation coefficient as a distinguisher, we can see that after the first error there is a distribution change in this sequence. So if an attacker could could automatically find this distribution change, they will be able to also to correct the first error, and so to improve the effectiveness of the attack. So a popular approach to do so is to set a threshold over the distinguisher, so that whenever the distinguisher falls below this threshold, an error is detected. But however, the problem with this approach is that the two distributions might be overlapping, as in this case, and this would cause a large number of false errors to be detected. For this reason, we have implemented a new solution which is more effective for error detection and correction. So we add a few more steps to the pipeline of sequential attacks, and we do an error detection, which is a change detection test, a statistical test, to find distribution changes in the distinguisher sequence. And when a change is detected, we activate an error correction procedure, which I'm going to explain. So for the error detection, we employ a statistical test, which is an online change detection test, which is much more powerful than thresholds to detect distribution changes, because it examines the distribution between different windows within the sequence. So it is more powerful, and it is a statistical test, so we are able to control the false alarm probability, which is also very important, as we said. The correction strategy consists of a brute force search over a small window centered at the detected change point. For each possible combination in the brute force window, we go on with the attack for a few more steps, and we expect to find that when the combination is wrong, the distinguisher will follow different distributions before and after the brute force window, while when the key is correct, we will have the same distribution before and after, so which is the same idea as our error detector. So again, we will use a statistical test to compare the distributions of the distinguisher before and after the brute force window, so to find the correct combination. To deal with false alarms, which might occur in any statistical test, we decided to exclude the brute force window from this monitoring. So we compared the distinguisher just before and after the brute force window, but not inside this window, because false positive can be triggered by a small set of unusual distinguisher values, which are obtained even though the key is correct. So we remove this window and we compare only the distribution before and after the window to find the correct combination. We have implemented and tested our error detection and correction methodology on two different sequential side-channel attacks from the literature. The first is a horizontal correlation power analysis, and the second a timing attack, both against the RSA 2048. And as we can see from these plots, which represent the success rates of our attacks, we can say that our strengthened attacks work much better than the original counterparts. And we also tested this threshold-based technique from the literature, which is far less effective than ours. And in particular, in the power attack, we observed that our strengthened attack is more robust with respect to noise. And on the timing attack, it requires much fewer timing measurements to succeed. That's more or less it. Thank you very much for your attention. If you have any questions.
Are there any questions from the audience? I don't see anything on the chat right now. And while we were waiting, I did have a question. So is there any heuristic involved in this process, like the gamma threshold? Is this all part of the statistics, or you still need to decide on a certain confidence or like statistic level, like the gamma in the paper?
Sorry, we actually don't use the threshold because it's not effective. We use another statistical test.
Yes, but there's still a gamma in this, where the distribution has like a
yeah, of course.
Triangle shape.
Yes, the thresholds have been computed for this statistical test, and they have been computed through Monte Carlo simulations, because the statistic is non-parametric, so it does not depend on the distribution of the data. So the thresholds are pre-computed.
So it's basically like a generic technique.
Yeah, it works for any distribution.
So there's a question: what is the size of the brute force window? How many elements do you need to get a reliable statistical test?
Okay, in this case here, it depends on the attack, of course. In this case, it was the horizontal correlation power analysis attack, and we actually took we start from a very small window of 3 elements, and we increase it when the correction is not successful, up to a maximum of 9 elements. So since they are single bits, we'll have maximum of 2 to the power of 9 combinations to search. And we go on with the attack for 30 steps in order to have enough samples to compare the distributions for the statistical test.
There's another question, maybe I have time for one more. Are there limitations on the implementation type, like left-right sliding, variable window? And did you get a feel for what different implementations did, like Wolf, SSL, or embedded TLS?
I'm sorry, I can't hear you very well.
Okay. Let me try this. Are there limitations on the implementation type? So, like, did you try different implementation types, like left-right sliding window, variable windows? Did you get any feel whether it like makes a difference what kind of implementation you put in this methodology? Or did you just try a single?
No, actually, we tried, there are 3 different implementations of the RSA. We tried square multiply always, and multiply and square, so the opposite way of the in the loop, and also a sliding window implementation. But it really depends on the attack, not much on the implementation of the algorithm. If a sequential attack, so something like in this scheme is possible, then our methodology can be applied. So it does not depend much on the implementation of the target algorithm, but on the kind of attack you want to strengthen.
Okay. Okay. Thank you, Luca, for your presentation. Then Kimmo, over to you.
Yes, sure. Okay, so the next presentation is the long and winding path to secure implementation of global platform SCP-10. It's authored by Daniel de Almeida Braga, Pierre Fouque, Mohamed Sabt, and the speaker will be Daniel de Almeida Braga. So please.
Hello, everyone. Can you see my screen?
Yes.
Okay, thanks. So thank you for the introduction. I will be presenting a joint work between Pierre Fouque, Mohamed Sabt, and me from IRISA in Rennes. So this work is about attacking SCP-10, which is a secure communication protocol designed specifically for smart cards by a global platform. So this kind of protocol are used to establish a secure session between a smart card and what we will call an off-card entity. Unlike some previous secure communication protocols, SCP-10 introduces a public key infrastructure during the key exchange, which is nice, but it also comes with a whole lot of new potential vulnerability. Namely, if we consider the need to optimize all computation and all processing on the card side, because they're really constrained and low computational power devices. So we decided to take a look at the specification, namely in the key exchange part of the specification, and try to look for some flaws and some blur, which could lead to some vulnerabilities. And we found quite a few, which allowed us to mount 2 independent full key recovery attacks and the signature forgery attack, which allowed to impersonate the smart card in all future communication. So we implemented and publicly disclosed all a proof of concept for each attack and the secure version of SCP-10, which implements all mitigation we suggested in order to estimate their overhead. So all of our attacks assume an attacker in a simple active man-in-the-middle position, so the attacker will be able to intercept, read, and modify any messages transmitted between a legitimate off-card entity and the smart card, but the attacker have no physical access. So we do not consider any physical side channel attack or any fault injection attack and so on. We mainly focus on the key transport mode in the key exchange because after some setting messages and the classical certificate exchange, the session keys are directly transmitted by the off-card entity, encrypted with the card RSA public key. And the proper authentication only comes after and is optional in the card side in order to avoid some heavy computation. So we noticed quite a few issues in this particular APDU. Since the padding is called PKCS1 version 1.5, which could be an issue on its own, but it's explicitly described to be deterministic. So this leaves only very few unknown bytes in the padded message, and with some assumption on the public key, which we believe to be reasonable given the current guideline on smart card implementation. An attacker will be able to recover the payload using the famous Coppersmith attack. And with some optimization in the attacker is even able to recover the session key before the smart card decrypts the payload. And this is a fully offline attacks once the attacker has intercepted the message. So all computation can be performed without any contact with the card. The second vulnerability also stems from the padding, but also the complex processing of the APDU on the card side. So we all know that this kind of padding is quite prone to format oracle attack, as shown by the last 22 or so years of Blechen-Bahar attacks in the wild. But here the padding processing is immediately followed by some data parsing on the card, which will yield a significant timing difference if an error is returned before the data can be parsed. And there is no mention of constant time implementation, no guidance whatsoever in the specification. And finally, since there is no key isolation whatsoever, this padding oracle can be abused to forge a valid signature. So for instance, a valid certificate issued by the card, which will allow to impersonate the card in all future communications. So most of the mitigation we suggested do not impact the overall performance, except, of course, for the key isolation, since we need to transmit 2 keys instead of 1 and verify 1 signature more than in the legacy protocol. But this is really a one-time overhead, since after a successful session, the smart card will save the certificate and consider the key as valid and verified. And in all future communications, the overhead become much more reasonable. So of course, we discussed all of this with Global Platform, which were quite responsive. They released a half-fixed amendment to the protocol this July. So there are still a few issues, and we're in touch with them in order to fix them, but it's in the pipe, and the final version should come out quite soon. So if you have any question, I will be glad to answer them. You can take a look at our implementation, so proof of concept and secure implementation in our GitHub link if you want. Thank you.
Yeah, there is one question on the chat. Do you expect a similarly winding path for other SCP versions, like number 11?
I hope no, and we briefly took a look to the SCP-11 specification, which is, well, for 1 point clearer than SCP-10 and less prone to error, because they really rely on existing specification to implement the sensitive parts. They point to some NIST documentation and so on, and there are really less trap in the proper implementation. So we expect much less issue with this version.
Okay, thank you. There's no more questions, so I think we can move on to the next speaker.
Thank you.
Thank you.
Let's try to take this Blue Thunder paper now, so that I will share this, my screen, and Tianlin can then say when he wants to change the.
I change another computer, and may I try it again? And
okay, yeah, it would be better that way. So let's try it first.
And
okay, and now we can actually see it. So yeah, this is the best way to do it. So
yeah,
please go ahead.
Yeah, thank you. Hello, everyone. Today, I will be talking about our paper called Blue Thunder, a second-level directional predictor-based side-channel attack against SGX. Intel's SGX is a hardware-based TEE which has strong security guarantee. However, recent research has demonstrated that SGX is vulnerable to attacks. Among these attacks, BPU-based side channels are getting considerable attention. First, BPU-based attacks can defeat most of current SGX protection approaches. Second, BPU-based attacks can identify instruction-level control flow information inside an enclave, while other attacks can only recover page-level or catch-line level secrets. The pattern history table is the main component in the BPU to be abused to conduct side-channel attacks against SGX. However, current PHT-based attacks require a large number of branches for activating the vulnerable before each detection, which causes considerable training overhead and limits the temporal resolution of this attack. If the application runs fast, it will be hard for this attack to catch up with the target application. As a result, several secret bits may be missed during the attack. In this paper, we propose Blue Thunder, a new PHT-based attack which can reveal fine-grained control flows of an enclave program running on real SGX hardware. To the best of our knowledge, this is the first side-channel attack on the second-level directional predictor. Several new technologies are proposed in this paper. Implement Blue Thunder and evaluate it on several case studies. Experiments show that our attack can outperform the latest PHT-based side-channel attack, which is brain scope by 52 times. Specifically, our implementation is able to derive the RSA private key with 96% accuracy in a single run. We stress that hardware-based countermeasures against Blue Thunder attacks need to be taken in order to prevent large-scale explanation of Blue Thunder. We assume a standard SGS threat model in which the attacker has full control. Also, the attacker has several. Now we turn to present Blue Thunder. This is the overview of our attack. The Blue Thunder attack aims to obtain the fine control flow of an enclave program by manipulating the predictor. In general, the Blue Thunder attack consists of the following two stages: activating the second-level predictor and leaking secrets. In stage 1, we activate the second-level predictor by imposing several mispredictions on other predictors. Executing the target branch with a carefully designed direction vector can mislead the BPU to make such mispredictions easily. In stage 2, we are trying to leak secrets using the second-level predictor. Two steps are included: and abusing collisions. First, we try to establish PAT entry collisions between the victim and the attacker. We also propose a novel method for constructing a specific branch history to achieve this goal. Our history construction is based on the observation that the branch history update can be controlled by manipulating the last 2 bits of branch's destination address in Intel processors. Then we abuse the entry collisions established. We adjust the branch directions of the target branch dynamically by setting the execution direction of the target branch just opposite to the predicted direction. By probing the state changes of these collision entries, we can infer the control flow of the enclave program as well as the secrets in it. We launch Blue Thunder attack against the embedded TLS library, whose RSA algorithm is vulnerable to control flow attacks. This figure demonstrates the execution directions of the attacker's target branch. We also compare Blue Thunder with the latest PHP-based attack branch scope. The result shows that the speed of Blue Thunder is about 52 times faster than branch scope, and their accuracy is similar. You can get more information in the paper. Thank you for listening, and I will be happy to take any question.
Any questions from the audience? I had a question not really technical, but I saw you contacted Intel. Was there any response so far? Did they?
Yeah, we have already sent an email to Intel and tell them that this vulnerability, and they respond to me and said that they have already received another email, which is branch scope, and this vulnerability is pretty similar to branch scope. And they said that they will consider such vulnerabilities in the future. Yeah. Sorry.
Sorry, sorry, I was muted. My apologies. How portable is the Blue Thunder attack across platforms?
We used to try this vulnerability, this attack on ARM platform, but however, it does not work because we have already met some problems. For example, the ARM use other different ISA, I mean the instructions, and the attacks we implemented on Intel platforms, which cannot work on ARM platform. We have not tried on AMD platforms.
Okay, thank you. Oh, and then maybe one more. Do we have time? Yeah, maybe one more. Does the collision algorithm depend on the processor model?
Yeah, it depends on the processor model. Because different architecture may have different algorithm to index the entries. So if we want to make the entry collisions, we need to first try some experiments to infer the indexing algorithm, and then we can make the entry collisions easily and successfully.
Okay. Thank you.
Thank you.
Yeah,
Thank
Kimo,
you.
over to you.
Sure. So we have 2 presentations left in the session, and the next one is high-speed masking for polynomial comparison in lattice-based schemes. It's authored by Florian Bach, Clara Baglialonga, Tobias Oder, Tobias Schneider, and Tim Günescher. And Florian will give the presentation. So please. Florian, are you muted?
Sorry, you hear me?
Okay, I can hear you.
Okay, thanks. Thank you for the introduction. Similar to the first paper in the session, we looked at lattice-based key encapsulation mechanisms that use the Fujisaki-Okamoto transform to achieve the CCA security. And maybe I start a presentation. We looked at the defense side. So we looked at how to protect against side channel attacks using masking. Specifically, we looked at one part of the decapsulation algorithm, which is a comparison step that is necessary in the Fujisaki-Okamoto transform. And if we want to mask the decapsulation, then we also have to mask the comparison step. And this comparison itself is very straightforward and cheap in the unmasked case, but if you want to apply masking to it, it becomes expensive very fast. And this is the problem that we wanted to address in our work. So we proposed a new algorithm for the mask comparison, which works at high masking orders. We give a theoretical security proof. We show that it's really fast, even at high orders, and doesn't need much randomness, and give some performance evaluation figures for different parameter sets, as well as a practical security evaluation. So the overall decapsulation algorithm we looked at looks like this. This is a New Hope. The decapsulation looks kind of similar for other lattice-based schemes, but this was our main benchmark, so we're looking at this here. We're only looking at one part, so we have A prime as an input, which is a polynomial. In the case of New Hope 1024, it consists of 1024 coefficients. It's input to the decryption. Then the output of this is fed into a random oracle as well as into a re-encryption. And the output of the re-encryption is then compared with the original input. So we can prevent the types of attack that were discussed in the first paper. So we are looking at this comparison step, and we have 2 inputs here. We have one polynomial A prime consisting of k coefficients, and the output of the CPA re-encryption also k coefficients. But as we want to prevent side channel attacks, the coefficients here are masked, and typically we use arithmetic sharing because of the structure of the decryption encryption algorithms. Okay, so for the comparison algorithm itself, it works on the core idea that we perform the comparisons on multiple coefficients at the same time. And to do this, we split them into sets, X sets of size L each. And then we calculate kind of a masked sum. So here we use fresh randomness R1i and R2i and sum over the coefficients. And please note that this sum is not over the shares, it's over the coefficients. And also interesting to note maybe is that the randomness is the same for all shares. So it's 2 random words per coefficient, and it's the same randomness for all shares. And this also means then that the randomness requirement is independent of the masking order. Okay, and after we computed these masked sums, we can unmask them, just by summing up the shares. All computations are, of course, modulo Q, but I left it out here. And we can then rewrite the sum to the thing you see on the right. This is a sum over the coefficients plus n times R1i times R2i. And we don't see any shares here anymore. So this is a sum over unmasked coefficients, which are kind of blinded by the randomness. What we can do is then compute the same sum over the unmasked input, so the A prime, and then just compare the two. And then if all of the unmasked sums are equal, then we say the coefficients were equal, and if not, we say this is not the case, they are not equal. Okay, to the performance of this algorithm, we have a benchmark here by Oda et al., which implements the CCA decapsulation in 25 million cycles. And the comparison alone takes around 480,000 cycles. So this is not too much overhead, but the comparison algorithm that was used there cannot be extended to higher orders easily. So there's a more general approach which uses arithmetic to Boolean conversions. And this can be extended to higher orders, and this takes 4 million cycles in the 2-share case, in comparison to 250,000 cycles that we need in the 2-share case. And if we increase the masking order, you see that the speed up only rises. At 5 shares, we had almost a speed up effect of 100. And this is because the complexity of the A to B conversion-based approach is quadratic in the number of shares, and ours is linear. So yeah, we did also benchmarks for other parameter sets, and the picture is basically the same. And the time for randomness generation is also included here. But this is another table, just the randomness requirements, and you can also see that we need much less randomness when compared to the A to B based approach. Okay, to conclude, we have this new higher order comparison, which allows secure and fast comparisons at high masking orders. We have a complexity which is proportional to the number of shares and the number of coefficients. And in the paper, there's a detailed security proof as well as practical evaluation using TVLA. And that's it. Thank you for your attention.
Thank you, Florian. There is a discussion going on the chat. I'll just mention the question. So if anybody's interested, then they can go there. I think Tobias is on it. The scheme does not hide the information if part of the polynomials to be compared are equal. Couldn't this be a problem for New Hope? And what if an attacker changes a valid A only in parts and is only interested if U stays the same? Oh.
Yes, if the polynomials are equal, then it doesn't work. Yeah, that's correct. But then also the attacker doesn't gain any information, because the assumption is that he then can forge valid ciphertexts. And yeah, if you can do that, he has broken a scheme already.
Okay. And then another question, did you also implement a higher order masked sampler?
No, we didn't look at the sampler. We only focused on the comparison algorithm.
Okay. And then maybe one more. Regarding the security proof, what does the security statement say?
The security statement, I'm not sure what.
Mehdi, what do you?
I mean, the security proof is in a probing model. Yeah? So we show that we can basically simulate all intermediate values without using all input shares, and therefore are secure against a teeth order attack, let's say.
Okay. That seems to be a good answer. Yes. Mehdi, thanks you. All right. I think that concludes the questions for this talk. Then let's move to the last presentation.
Okay, so
Thanks,
the last talk is about power analysis on NTRU prime, and it's a paper by Weilun Huang, Jianpeng Chen, Boying Yang, and the speaker will be Weilun. So please.
Wait a moment. I'm now change the preference, the system preference about the security. Can you now see my screen?
No, not yet.
Can you now see my screen?
No.
Okay.
We see your
let me restart the
video.
Change preference. Okay.
Pardon?
Restart the Zoom because I just changed the system preference and changed the permission to my Zoom to share screen, right?
Yeah, please start sharing. Yeah. Okay, let's see if he comes back soon. Okay. Okay, welcome back. Okay, now we can see it, so everything is okay. Please go ahead.
Can you see the slide?
Yes, yes, we can.
Great. Let's start. Hi, everyone. I'm going to introduce you to the work Power Analysis on True Prime. I'm Weilun Huang, and the other two authors are Dr. Jianpeng Chen and Dr. Boying Yang. We come from Academia Sinica, Taiwan. First, let's go through a brief review. We propose 3 single trace power analysis methods against fault scanning. We apply them to a reference implementation, an optimized version with SIMD instructions, and several protected implementations of untrue prime polynomial multiplication. We are interested in the P by P polynomial multiplication over Garfield Q between a general knowledge C and a ternary weight W secret F. The first input can be public key or ciphertext, while the second input is session key or private key. It is clear in this diagram that the most sectional affirmative part is the calculation of the middle output coefficient. Therefore, if not specified, all power traces correspond to this part. Here is a photo of our measurement setup. We first run the target implementations in C and ARM assembly on Cortex-M4. Chips Rely 2-power version helps generate random inputs and measure target power consumption. Then we start our statistical analysis programs in Python 3.6 and C++ on a MacBook Air to analyze these power traces. Horizontal in-depth correlation power analysis. In in-depth CPA, we compute the ideal power sample sequence with different intermediate variables from one single input. Its real-world counterpart is from different timings in one single execution. Compared to traditional CPA, in in-depth CPA here, each intermediate state helps more than reveal one new perfect key coefficient. It can reveal several, it can verify the correctness of several previously revealed perfect key coefficients. To exploit this dependence and also slow down the exponential increase of candidates to test, we use the extend and prune framework here. Unfortunately, some perfect key coefficients at the end of the block may go wrong. In the current block recovery, they are related to very few intermediate states. So these tail errors may lead to a better correlation due to the noise. However, in the next block recovery, the initial intermediate state of the middle output coefficient must be wrong. So no hypothesis, not even the correct one, can lead to a good correlation, and there will be no survivors and epic fail. Luckily, no survivors in the current block recovery also signals the tail errors in the last block recovery. And thus we can roll back by heavy block to correct these tail errors. They are now right in the middle of the current new block. In in-depth CPA, candidate pruning can be ineffective because each M coefficient block only corresponds to M power samples. Therefore, we can learn from horizontal attacks and observe some near the middle output coefficients. These output coefficients have almost as many intermediate states as the middle output coefficient. So by observing L-1 more output coefficients, we can have L times as many data almost. Online template attacks. In online template attacks, we acquire the single target trace first. We partition this single target trace into pieces. Each piece corresponds to one multiply and accumulate. Then we start to generate 3 template traces for the first perfect key coefficient recovery. They indicate the perfect key coefficients to be 0, 1, or -1. The online template attacks will then compare the first piece of the target trace with each of the 3 template traces. The closest template trace in terms of Euclidean distance can give us the optimal guess. We then update this guess to our knowledge, and according to this new knowledge, we start to generate the next 3 template traces for the second perfect key coefficient recovery, and so on. Here is a chosen input offline variant of online template attacks. First, we set the input ciphertext C to have p identical coefficients. Therefore, now each intermediate state of the middle output coefficient is a multiple of C sub 0 modulo Q. Since the W non-zero perfect key coefficients, 1 and -1 are randomly distributed, we need much fewer template traces to mount an attack. If we further let the template generator accept legitimate perfect keys, then we can set the F star to be 0, 1, 0, 1, 0, 1, and so on, or 0, -1, 0, -1, 0, -1, and so on. We then set the C star to be the input ciphertext C, except that C star sub 1 can be C sub 0 or C sub 0 modulo Q times -W modulo Q. Now the template generator only needs 4 executions to build all the templates we need. Chosen input simple power analysis. There are 2 commonly used countermeasures for intro-like crypto systems. The first is to randomly initialize each output coefficient and at the end of each output coefficient calculation, we subtract this random offset from a result. And the second is to randomly access input coefficient pairs during each output coefficient calculation. Unfortunately, none of these countermeasures are effective when the adversaries can choose the input ciphertext. Take countermeasure 2 as the example. We first observe the output coefficient calculations of degree 0 to p-1 and set the input ciphertext to be a constant C sub 0. We then partition this single low power trace into pieces. If the perfect key coefficient of degree I is non-zero, then the ith piece of the target trace should be discontinuous. And there are only two kinds of discontinuities, as there are only two possible values of non-zero public-key coefficients, 1 and -1. Now let's talk about some potential applications of our methods. Our methods may apply to all identity crypto if their secret coefficients also come from a small set of possibilities. As for other modification algorithms, our methods may work for multi-level Karuzuba ending with product scanning. Thanks for your listening. And here is time for Q&A.
Thank you for the presentation. Are there any questions from the audience? There's a question. Have you also looked into attacks on protected implementations?
Excuse me?
Have you also looked at attacks on protected implementations?
You mean the attacks against protected implementations, right?
Yes.
Sure. For example, here is there are two protected implementations, and they were commonly used for NTRU crypto systems like NTRU Encrypt or of 2000 to 2010 version of NTRU Encrypt or some other NTRU open source implementation, and therefore we devised and we proposed the chosen input simple power analysis to analyze these two countermeasures. And the rather simpler example is the countermeasure 2, which is the example in this slide. And in the complete slide, or in the more complete version of our slide, we also implement the chosen input simple power analysis against countermeasure 1. So there is at least one power analysis method in our paper that can analyze the countermeasures commonly used for such crypto systems. Is this what you want?
Yes, thank you.
Thanks.
All right, I think this concludes our session.
Yes, indeed. So maybe thank all the presenters.
Thank you very much. Bye-bye.
Okay, so thank you very much, everybody.